So the purpose of this particular video is a real quick crash course on a topic called mole ratios, and this is going to set us up for our next topic, which is called stoichiometry. In stoichiometry, we need to have completely balanced chemical equations to start, and so for our purposes, all of these equations are going to be balanced beforehand, so you don't make any mistakes in doing those, and we're going to learn how to write something called mole ratios. And so on this chemical equation that's balanced, what I have here is indicators on here of how many moles of each substance and product that I either need or make. And so I have 1 mole of carbon dioxide. Remember, the 1 is never written as a coefficient in front, just having the chemical formula is sufficient. And 2 moles of lithium hydroxide, and 1 mole of lithium carbonate, and 1 mole of water. And I can write something called a mole ratio. Now, ratio is just one thing over another, and so one ratio I could compare is 1 mole of carbon dioxide to 2 moles of lithium hydroxide. And what that's telling you is that for every 1 mole of carbon dioxide, I need to have twice as much lithium hydroxide, twice as many moles. And that makes sense if you think about it. If I had 1 molecule of carbon dioxide, I need 2 molecules of lithium hydroxide. I need twice the number of things, twice the number of particles. You can also write the mole ratio the other way because it's just a ratio, and so they're equal both ways. And so I could compare 2 moles of lithium hydroxide to 1 mole of carbon dioxide. I could also compare 2 moles of lithium hydroxide, 2 here, to 1 mole of lithium carbonate, or 2 moles of lithium hydroxide to 1 mole of water. And I can write the reciprocals of those as well. So the question is now how do we use these things? Because writing the mole ratios is fine and dandy, but we need to be able to set up proportions. And some of you are going to be used to setting up proportions, but I prefer to use the factor label method that we've learned before in setting up conversion factors. And so we're going to do a little practice problem. If you want to take out some paper and take note of it, or just watch it, doesn't make any difference. We can give this one a shot. So here's one where I have a balanced chemical equation, just a standard decomposition reaction, heating up some mercury oxide, and so I have 2 moles of mercury oxide will break down into 2 moles of mercury and 1 molecule of oxygen gas. And the question is, if 3/4 of a mole of oxygen were produced, how many moles of mercury were made? Now, a lot of you can just kind of think your way through that problem and say, okay, if I'm talking about oxygen and I have 0.75 moles being made, I'm going to make twice as much mercury. So if you think about that, twice as much would be 2 times 0.75, and so that's 1.5 moles of mercury getting made. And that's fine, but a lot of times the numbers don't work out so nice that you can do them mentally, and this happens to be a good starter here. So let's do this the factor label method. And so our given is going to be 0.75 moles of oxygen. So we put in 0.75 moles of oxygen on the bottom. Well, what goes in on the outside? What goes on the bottom of our conversion factor here? Well, I have moles of oxygen out here. Now, in the past, we've only dealt with one substance, and now that we have multiple substances that we're going to be dealing with, we do have to keep track of what substance we have. So I have moles of oxygen, so moles of oxygen are going to have to go to the bottom. And all I'm going to do in the parentheses is I'm going to pull the numbers out of the equation, and so I have a 1 in front of O2, and so I put a 1 in for O2. So there's that goes. Here's my moles of mercury. And I pull the 2 from HGO in front of here. So the numbers that always go inside the parentheses are just the balancing coefficients on your chemical equation, assuming it's balanced right. And so now you can see we have 0.75 times 2, which is exactly what I said it was at the beginning of this problem. It's twice as much oxygen, and so we have 1.5 moles of mercury being made. Now, you have an assignment on Teams, and that assignment has a problem up at the top, and so I thought we'd just do the first part of that problem together. And so if you want to pull that up on Teams to look at it, or you just want to look at the video here, I'm not sure how the best way that you can do it is, but here's the general problem. It looks a little bit different on your papers. Well, not really papers because it's digital, but on the Word document that I have posted. I have a reaction of, this would be carbon disulfide and oxygen, making carbon dioxide and sulfur dioxide. And the problem starts off saying I have 4 moles of oxygen reacting. How many moles of CS2 are needed? How many moles of CO2 are needed? Made. And how many moles of CO2 are made? And so we have our products over here on the right, and so we're just going to calculate how much CS2 do I need to react. And so now the numbers aren't quite so easy. Now some of you could probably mentally figure it out. And so this is saying that for every 3 moles of oxygen, I need 1 mole of CS2. So I need 1/3 the amount, okay, of CS2 as I do oxygen. So if I'm starting with 4 moles of oxygen, that is the given. That's going to be the given in all these problems. So I have 4 moles of oxygen. What goes to the bottom? Well, moles of oxygen are going to go to the bottom, and I'm going to bring this 3 along with it. Remember, the numbers that go inside the parentheses are just from the balanced chemical reaction. So I have 3 moles of oxygen. What goes on top? Well, I'm interested in CS2. And so there's a 1 in front of CS2, and so I put 1 mole of CS2 on top. And now you can see, look, I said it was 1/3 the amount. Well, you have 4, you have 1/3 of that, and that's exactly what you're doing here. You're taking 4 divided by 3, or 4 multiplied by 1/3, however you want to think about that. So 4 divided by 3, I'm going to need 1.33 moles of CS2. The given is the same for sulfur dioxide. Set it up. I have 4 moles of oxygen, just like I had before, and I would always go with what the given is. Moles of O2 are going to go on the bottom. The 3 from the chemical equation is going to follow it. But this time we're interested in SO2. So the coefficient in front of SO2 is 2. So I bring in 2 moles of SO2 here, and now it's 4 times 2 divided by 3. Well, that ends up being twice the amount that we had in the first problem here, because this is just a difference between a 1 here and a 2 here. And so 4 times 2 is 8, divided by 3, and you're going to get 2.67 moles. If you don't believe me, oh, the calculator went off. I've got to turn it on because otherwise the batteries run down. I did 4 divided by 3 times 2, and 2.67. Same given is given in CO2. We have 4 moles of oxygen. And so moles of oxygen are going to go to the bottom, and I'm going to bring the 3 from the chemical equation. I'm interested in carbon dioxide this time, so there's a 1 in front of CO2, and 1 mole of carbon dioxide. And look at that, the setup is exactly the same as it was for the first one. It's the same numbers, it's just different substances, because this equation says that for every 3 moles of oxygen, I need 1/3 the amount, or 1 mole of CO2. And so all we're doing is setting up proportions. And so if you're used to setting up proportions, that's fine, but I think sometimes proportions get a little bit confusing. If you understand this factor label method and how these units will end up canceling out, which I didn't cancel them out in here, but you know that moles of O2 cancel with moles of O2 on all of these, and so we're always left with moles of the substance we're interested in. 4 times 1 divided by 3, 1.33 moles of carbon dioxide. For the end of break, I would like you guys to have the sheet that I have posted on Teams answered. You can put that on a separate notebook paper, and I'd like to discuss that on the Monday that we return. You're more than welcome to watch this video multiple times. And again, I'm in the library, but unfortunately I don't think I have any breaks at all to talk to you guys. So have a great spring break, and I will see you next month. Thank you.